Yeah, so hi, Harry Kalodner. I'm here from Princeton University to tell you about a platform we've built called Arbitrum, which allows for scalable private smart contracts and joint work with my co-authors up there. So I'd like to start by just telling you how we think about smart contracts in terms of what they are and what they're good for. So assume we have Alice and Bob want to interact with each other, but they don't trust each other. So what they can do is they can use a smart contract to mediate their interaction. So they agree on some rules that they put into code that they're happy to both follow in order to interact. And then they create a smart contract that will obey that code. And for our purposes in this presentation, I'll be calling this a virtual machine, since that's what it really is. And so they can interact with that virtual machine. They can be guaranteed that the virtual machine will operate correctly. And the virtual machine is a first-class actor in the system, so it can hold money and it can send and receive messages. So the main invocation of smart contracts that people are familiar with is Ethereum. And Ethereum has some very substantial issues with scaling. So the way Ethereum reaches consensus over smart contracts is that every miner has to run every single contract and execute every single step. And the way that this works at all is that transactions are metered, and users have to pay gas for computation and storage. And this is necessary to prevent denial of service and leads to high cost for contracts. Moreover, the total gas limit that can be included in the system is limited by the throughput that a single miner can perform for one block. And so complexity has to be capped at a fairly low value by the global gas limit. And further, the fact that every miner has to be able to evaluate every contract means that all contract and data is public. And so you can't really get any native privacy with this sort of system. So we asked the question, can we do better than this? Can we scale smart contracts? And I'd like to say specifically in this talk, when I'm discussing scaling smart contracts, we're interested not in the consensus layer, where there's been a lot of development, but in the smart contract layer. So assuming that we have an underlying consensus system already, can we have the consensus system implement smart contracts in a way that allows for further scaling? So that's what I'm going to be talking about today. First, I'd like to mention some alternate approaches to this problem, since there has been some work in this area. First, snarks. Snarks provide quite low on-chain costs for verifying contracts, but they require trusted setup for every contract, which can be difficult and expensive to pull off. And off-chain proving for snarks is very expensive, so it limits how many people can actually be users of these contracts. Next, we have incentivized verification, best displayed by TrueBit. This handles a lot of scaling issues quite well, but it suffers from a lack of privacy for the same reasons that Ethereum does, in that verifiers need to have access to your contract information to verify it. And further, in our paper, we demonstrate some serious incentive compatibility problems with the protocol, which you can read more about in the paper, although I won't talk about it more today. And finally, we have state channels. State channels function by assuming that there will be unanimous agreement among all contract participants in order for the contract to do anything, which is an assumption that is very difficult to pull off and kind of rules out a lot of applications. And further, in the case of a dispute between those participants, dispute resolution is extremely expensive. And so that kind of is very limited in how you can scale. So how does Arbitrum actually beat these systems and really bring scaling to really make scaling possible? So Arbitrum uses a combination of three different techniques. Protocol design. We designed the protocol such that there's an optimistic case and a pessimistic case, where the optimistic case can function extremely quickly, and where the pessimistic case is fairly efficient as well. We then use incentive design to make sure that the optimistic case will execute almost all of the time, so that the overall system will be quite efficient. And we have a custom virtual machine architecture that makes sure even in the pessimistic case, everything executes quite cheaply and efficiently. So how does this work? I'd like to start by talking about two major roles in the Arbitrum system that are key to understanding what's going on. So first we have the verifier. And the verifier is the term that we use for the underlying consensus mechanism. The verifier could be any number of different parties depending on the system. It could be Bitcoin-style mining with proof of work. It could be a central authority. It could be BFT protocol. But we're agnostic, and so we just call it the verifier. Next, we have managers. So when you make a VM, you give a list of managers for it. And the managers are responsible for keeping track of the VM's computation and data. And there's one very key guarantee in Arbitrum's system that's important for understanding the system, which is the any trust guarantee, which is that if at least one manager of the VM is honest, then the VM will execute correctly according to its code. And that's basically the only trust that you need to have involved in the system, and we'll see how it plays out in practice. So let me give you an example of how this would work. Say Alice and Bob want to play a game of chess, and want to bet on a game of chess in particular. So they agree on a set of code that represents the rules of the chess game and create a VM using it. The VM is responsible for receiving alternating moves, verifying the validity of the game, and paying out to the winner. But in this situation, we know who the verifier is, the underlying blockchain, and we know who the participants in the contract are, Alice and Bob, but who are the managers? Well, the very simple answer to that is that Alice and Bob can themselves trivially be the managers. And that would mean that they would simply be responsible for making sure that the contract executed correctly, and I'll explain how they do so later. Alternatively, if Alice and Bob for some reason don't want to be a manager, they could simply hire a third party who they trust to be the manager of that contract and pay them out of band. So what do managers actually do for a VM? What does all this mean? Well, to start with, managers are incentivized to agree unanimously as to what a VM does. And if they all agree, the system simply accepts the assertion. And I'll show you what that looks like. So a unanimous assertion consists of a number of parts. There are a set of preconditions which state the expectation of what the current state of the machine is. There are a set of actions which are what the VM actually does while it's executing. And there's a resulting state. So you note that the assertion is only specifying external actions as well as a start and an end, but nothing about what happens in between. And this is broadcast to the blockchain, along with the signature of all of the managers. And after this is broadcast, assuming that the preconditions are correct, it's simply accepted. And this means that without doing any sort of work to verify the correctness of this, it's been accepted into the blockchain. And note that this easily satisfies the requirements of the any trust assumption because all of the managers have agreed. But what if they don't? So in this situation, we have disputable assertions. Any manager can make an assertion about a VM by themselves. And all they have to do along with that is deposit funds. Next, if one other manager disagrees, then they can issue a challenge against this assertion, where they deposit funds as well. And in a challenge, the party that's wrong will lose their deposit. And so we can ensure through this approach that the actual eventual execution will be correct, assuming there is an honest manager around to issue a challenge. So what do disputable assertions look like in practice? Well, to begin with, we have essentially the exact same model as a unanimous assertion, except in this case, it's only signed by a single manager. The assertion is broadcast to the blockchain, and a challenge period begins. During that period of time, any other manager can initiate a challenge. However, if there is no challenge, the assertion is simply confirmed, and the actions it specifies occur on-chain. But what if there is a challenge? Since that's the really interesting situation. So in the case of a challenge during the challenge period of the assertion, the challenger responds. They say, hey, this is incorrect. Somewhere in this assertion, something went wrong. I disagree with the result. Next, the creator of the original assertion bisects that assertion into two segments, into one assertion covering the first n steps of execution of the VM, and the second assertion covering the second n steps. And note, in this situation, the asserter is saying that while the original assertion specified two actions, sending some coins and sending a message, when it split in two, the message send occurred sometime during the first half of the execution, and the coins being sent occurred sometime during the second half of the execution. So this process continues. The challenger at this point it has to say either one or the other of these two halves are incorrect, since clearly if the whole thing was incorrect, one of the halves has to be. And so they challenge that half. The bisection continues between the asserter and the challenger at each step until we reach a single step of execution which is under dispute. And this step of execution, we've split the problem into as small a piece as possible, and so now we need to include some sort of way to prove the correctness of this step. And so one-step proofs are going to be a major part of the remainder of this talk. So the one-step proof has to somehow prove, given a start state, that the machine executed correctly to reach an end state over a single step of execution. And there's some important quantities we need to think about when we're talking about the one-step proof. So how big is it? Is it feasible to actually do this in practice? And how costly is it to create and verify? And I'll just say in Arbitrum, these come out to around 500 bytes. And so this is going to be a really efficient system. And the way we accomplish this is with a custom Arbitrum VM architecture. So in our architecture, all instructions can be emulated in small constant time, which means that it doesn't particularly, that your machine can execute any instructions and have an expectation that these will be able to be evaluated on chain. And one-step proofs are of small constant size and can be created and verified in small constant time. And so the proofs that I described earlier are going to be highly efficient. So there are four principles that four principles that the VM architecture implements, which allow these properties. The entire state is encoded in a Merkle tree, so it can easily be summarized on chain. The tree is of limited degree, less than or equal to 8. Every leaf is of limited size. And most importantly, instructions only affect the items near the top of the tree. These first three properties would be fairly easily achievable with any standard VM architecture, but this last one is really hard and unique. So in a conventional VM architecture, code and memory are viewed as simply long arrays of data. That's fairly flat. And a conventional way to create proofs over these would be to simply create a Merkle proof. Every single time you execute, for any instruction, you would have to prove that the instruction at the current PC is a given value, and you do that with a logarithmic size proof. In this case, I've grayed out the parts of the data that actually have to be broadcast with the proof. And any time a read occurred from memory, you'd also have to have a Merkle proof that that memory access was correct. And I'm going to show in the next couple slides how we solve these issues in Arbitrum with any one step only requiring constant size and time to check. So first I'll talk about handling memory. And I'm going to compare the conventional approach to how we handle things in Arbitrum. So where conventional systems would have memory represented in a large flat array, instead in Arbitrum we have memory consists of fixed size blocks, which we refer to as tuples. And these can reference each other. And so you can build up structures of tuples which include other tuples inside them. In a standard architecture, as I said before, the emulator would manage a Merkle tree over this memory to support proofs, whereas in Arbitrum, application-level code actually manages the tree in memory as a function of the machine rather than as a function of the emulator. And so what we have is, instead of having a read instruction in the VM, we instead would have a library call, which would go into this tree and find the proper leaf at the edge of it. And so in essence, what that means is we've taken something that before would be a single instruction that would have a log n cost, and instead we've transformed that into log n instructions, each of which can be executed in constant time. And so you can see how that plays in very well with our bisection protocol, where we already reduced logarithmically. And so now we've taken what used to be log n proofs, and now we have O of 1 proofs here. Next up, we have instructions. So normally with instructions, you would store source code in a list. But for Arbitrum, we instead store it in a stack. And this stack is going to be a nested stack of instructions where we have our first slot that points to the second, that points to the third, each of which includes an instruction. And you'll see a little bit more detail of what that means in a second. So instead of normally to go to the next instruction in a VM, you advance the PC. Instead, for us, you pop the stack, bringing the next item to the top of the stack. For jump, instead of just arbitrarily changing the PC, you replace the instruction stack with a new stack. And calling a function, you push the instruction stack to the call stack, and returning, you reverse that operation. So what does the Arbitrum VM look like? I've already mentioned the instruction stack, the data stack, and the call stack. What remains is also a static, which allows static values to be held by the VM, to be encoded with the VM, and a single register, which can be set and get dynamically. And to see what a one-step proof actually looks like for this VM, I'll demonstrate an add instruction here. So for the instruction stack, we've simply revealed the top item in the stack, which is an add instruction, and kept the rest hidden. We've had to open up the top 2 layers of the data stack in order to reveal the operands, and no other data has to be revealed other than hashes of the other items. And this can be proven given the start state, and then evaluated in order to calculate a new end state for the VM in order to verify the one step. So I've talked about scaling a lot. Now I'd like to mention privacy. So Arbitrum smart contracts are also private. Because in Arbitrum, the state of a VM is only revealed to the VM's managers. All that appears on chain is saltable hashes of the VM state, number and timing of steps executed, and messages and money sent and received by the VM, so kind of the minimum necessary information. We have an implementation written in Go code along with an assembly library, and we're working on programming tools. You can read more about this in the paper. Just to give a quick example of how Arbitrum, the performance you get with Arbitrum in practice, to give an example of iterated hashing where a VM just wants to calculate hash functions over and over and over, a single Arbitrum VM can perform almost 1 million SHA-2 hashes per second, compared to a native machine performance of 1.7 million, so close, but not close to native performance. And the real comparison is to Ethereum, which only supports around 10,000 hashes per second globally. And note the first line here, I say 1 VM, where multiple Arbitrum VMs can be running at the same time, a large number at the same time. And so the scaling here is really kind of unbelievable. Just in conclusion, so Arbitrum enables scalable private smart contracts. And we do this using a number of techniques: protocol design, incentive mechanisms, and virtual machine architecture. So thank you for listening, and happy to take questions.
No questions? All right, so I guess I'll ask a question. So can you summarize what the key technique is that allows you to get the performance benefits? I mean, of course, you described the whole thing in detail, but what's the key piece that allowed you to?
I mean, the fundamental key piece is simply the idea that the VMs only really run offline by the managers. The on-chain is only used for dispute resolution, which means that essentially we can run close to real time. With Ethereum, the global gas limit is set so that blocks take around 200 milliseconds to verify, and they need this because the consensus mechanism needs miners to be able to verify quickly. Whereas when you're running, whereas Arbitrum VMs don't really have any constraints at all there. So that's essentially what we need, is a way to handle disputes on-chain, so that on-chain we can settle arguments between the managers, and that's what a lot of what I talked about was.
Cool, thank you. Yeah, go on.
Hey, awesome work. I wanted to know if you thought about 2 things. So one is about using, I know you know what I'm going to ask some of these anyway, but have you thought about the incrementality features of Verisum from CCS a couple years ago, and also authenticated data structures instead of a flat memory file?
Yeah, I mean, it's an interesting question. I mean, I think our conception of this is very much not, that the computation's not being outsourced. That the managers are kind of in the kind of normal thought of the machine. The managers and the participants of the contract are the same parties, and so they don't actually necessarily want to have kind of the verifier even do, in the normal case, the work of maintaining an authenticated data structure. In the unanimous case, we want the verifier to not be involved at all. So I mean, I think we're certainly open to exploring further connections, and happy to talk more offline.
Okay, sure.
Yeah.
All right, any more questions? All right, let's thank the speaker one more time.